So this will be problem solving for substitution and elimination reactions. We'll start by discussing primary alkyl halides, followed by secondary, and then lastly tertiary. 1-bromopentane, in example A, is a primary alkyl bromide reacting with dilute methoxide in dimethylformamide, which is a solvent that promotes SN2 process. And you see that our major organic product is 1-methoxypentane. On the other hand, if we use a large concentration of methoxide and heat, we would expect E2. The 1-pentene would be our minor product, and we would expect that the major product would be the trans Zaitsev 2-pentene. If we take a good nucleophile like cyanide ion, we can displace the bromide and produce a nitrile via SN2. If we take another good nucleophile like acetylide anion in a solvent like THF, we can also displace iodide in a SN2 fashion and produce this internal alkyne 4-octine. Now, if we consider a primary alkyl halide with branching, which we could say is more sterically hindered, and a sterically hindered bulky base like potassium tertiary butoxide, we would see E2 elimination. Similarly, with DBN, we would also see E2 elimination from this primary alkyl halide. So as a summary, a good nucleophile and a weak base will promote SN2, whereas a strong base, which could be bulky, and with heat and or concentrated strong base will promote E2. It's important to note that if you instead had a secondary alkyl bromide plus a bulky base, we would expect the non-Zaitsev product to predominate due to the fact that the beta proton bonded to the more sterically hindered beta carbon plus a really bulky base would only have greater access to the less sterically hindered beta proton to give you the less substituted non-Zaitsev product. Now moving on to secondary alkyl halides, here we have S2-chloropentane, and we're reacting this with a good nucleophile, sodium thioacetate with the negatively charged sulfur atom. And we could also say that this is a weak base, and we're heating this in ethanol as our solvent. Here, our thioacetate would approach the alpha carbon backside, so we would see an inversion of configuration in the SN2 process. Sodium azide in dimethyl sulfoxide, a solvent that also promotes SN2, would perform a similar backside displacement of bromide to give you the inverted product of the azide compound. If you dissolve potassium hydroxide in methanol and add methane thiol, initially an acid-base reaction would occur between hydroxide and methane thiol to generate methane thiolate as your active nucleophile. This negatively charged sulfur atom is a champion of nucleophiles and would most certainly produce the SN2 product, again with inversion of configuration. If you have a dilute concentration of potassium methoxide, we would observe mostly an SN2 process. However, if you have a concentrated solution of sodium methoxide and you're heating the reaction mixture, we would expect mostly E2 elimination. If you start with this chiral secondary alkyl halide and you choose a really bulky base, we would also see E2 elimination, and we would most certainly deprotonate the beta carbon, which has the less sterically hindered proton. On the other hand, if you use a smaller base at higher concentrations and higher temperature, we would expect the Zaitsev's E2 elimination product to predominate. So here we have the two larger ethyl and methyl groups on opposite sides of the carbon-carbon double bond, and the one in which is more substituted and therefore more thermodynamically stable, followed by the Z isomer, and then lastly the minor isomer would be the mono-substituted 1-pentene. Along the same lines as L, if you choose a non-nucleophilic, sterically hindered bulky base like DBU in a solvent such as tetrahydrofuran, you will again pull off the proton of less steric hindrance to produce only the E2 elimination product. Remember, there will be no substitution from this sterically hindered non-nucleophilic base. So as a summary, secondary alkyl halides may undergo SN2 or E2 reactions. There is no SN1 or E1 due to the high in energy secondary carbocation intermediate. SN2 will predominate if you have a good nucleophile, which is also a weak base, whereas E2 will predominate if you have a strong base at higher temperatures and high concentration. The thing to keep in mind is that if you have a bulky reactant and or bulky base, you'll remove the less sterically hindered beta proton. Remember that beta elimination via the E2 reaction mechanism must occur in an anti-conformation. So for example, if you have trans 1-bromo-2-methyl-cyclohexane with reaction conditions that favor E2 elimination, our methoxide base can only remove a proton that's anti to our leaving group. So if we examine this polygon formula in a chair conformation, we see that the most stable has the bromine and the trans-methyl group disposed equatorial on our chair conformation. When we're heating this, we can produce in equilibrium via chair-chair interconversion or chair flip the higher in energy diaxial conformation. When it is in this conformation, it may then undergo E2 elimination. Note that the beta proton on the more substituted carbon, which would lead to the Zaitsev's product, that is the more substituted alkene, may not happen because the beta proton is syn, or it is cis, to our leaving group. Therefore, the only pathway that may occur via E2 is on the adjacent carbon that is less substituted with the proton that is axial and that is anti to our bromide leaving group. So the only elimination product via E2 is the less substituted cyclohexene. If you deal with the cis isomer, you now then have a beta proton that can exist anti because it is trans to the leaving group. And so under the same reaction conditions, we would then expect our Zaitsev's product to predominate via the E2 pathway. Moving on to tertiary alkyl halides. If we take tertiary butyl bromide in a concentrated solution of sodium methoxide with high heat, we would expect the E2 elimination process to occur. That is to say that there would be the anti-elimination of a beta proton with concerted loss of bromide ion. On the other hand, if you take a weak base with heat, we would expect the first step to be the displacement of bromide ion to produce the tertiary butyl carbocation, followed by a passive loss of the beta proton to give isobutylene gas via the E1 elimination pathway. If we controlled the reaction at lower temperature, we could then stack the deck, so to speak, to force an SN1 product to be favored. So if we ran the reaction again in ethanol, but only slightly elevated above room temperature, we could then expect the tertiary butyl ethyl ether to predominate. Now lastly, if we take the tertiary benzylic alkyl halide in refluxing methanol, we would expect displacement of our bromide ion to occur firstly to give a tertiary benzylic carbocation, which is resonance stabilized, and then the methanol nucleophile can add to either the top or the bottom face of our vacant 2p orbital, and after loss of the proton from the oxonium ion, provide a partial, or for your purposes, racemic mixture of benzylic methyl ether. This, of course, occurs in an SN1 pathway because there is no possibility for SN2 due to the steric nature of displacement that must occur backside in an SN2 process. So to summarize again, tertiary alkyl halides may undergo E2, SN1, or E1 reaction. There is no SN2 possible. If you use a strong base, at high concentrations and heat, we would expect E2 elimination. If you use a weak base, at slightly elevated temperature, you would expect SN1. And if you use a weak base with high heat, with greater entropy, we would expect E1 elimination.